Please go online and give us your feedback. Let us know what talks you liked, what talks you didn't like, what ideas we could have presented but didn't, if we miss anything. Please, your feedback is vitally important, and because of how small and kind of exclusive ShmooCon is, your feedback actually makes a real difference. It gets heard.
I'm sure we'll have loads of technical problems.
No, not with these guys. They tend to make it run really easily.
No, on our side.
Oh.
We're not very good at computers.
Oh.
Let me turn that off.
It's hard.
It's kind of like math. We have about 1 more minute.
Okay.
To let people filter in.
Okay, so just Command Tab.
Yep.
Yep.
Great. All right. I have been told to tell you, or at least I've been informed, that Brian's official title is Lifeform, but Mike's not sure whether he qualifies for that yet. It's, we have had a lot of talks. This sort of a theme of this conference has been on throwing real science at security, which I'm actually really excited to see. And this talk is another one in that line, the practical applications of data science in detection. Gentlemen?
Thanks.
I'll be back.
Sure. So luckily for you guys, we're gonna spare you a lot of PowerPoint. I think we've got 5 or 6 slides. Unluckily for you guys, we're going to use iPython notebooks, so you'll get to see some code and graphs as we run through the presentation. So thank you for attending Practical Applications of Data Science and Detection. I'm Mike Sconzo. That's Brian Wiley. This is probably a pretty good buzzword bingo talk, but hopefully you guys will learn things. So one of the main things I really want to emphasize, and I'll post a link in a second, try this at home. It's a lot of fun. We're actually going to release, and we did this morning on our GitHub, both iPython notebooks and some of the data that we use to actually perform the calculations, so everybody can go home and play to their heart's content. And by all means, if you have any questions, feel free to always reach out. So, brief introduction. When we talk about data science, what are we talking about? Well, we're talking about people who really like to tinker, people who understand, right, math and statistics, and people who understand things about a subject. Are they all one person? Maybe. In this case, it's 2 people. Brian has a crazy wealth of statistics and math knowledge. I have enough to be dangerous. I might be the subject matter expert, for lack of a better word, and we both really love to tinker with things. So this is a really good combination for both of us. Hopefully it pays off for everybody. So once again, just a slight brief plug. We're at Click Security. Luckily enough, they paid for us to come here. So thanks, guys. All right. So there are kind of 2 main things when you're running through data science. One is you have to have data to analyze. So great, how did we do this? Well, for our use cases today that we're going to be talking about, we used Bro, and we used SQL map and JBroFuzz to generate all the data that we're going to look at. Then to actually analyze the data, we use primarily iPython notebook because it has a really nice flow that you can begin to structure things through. And then we obviously use the Python pandas library as well as a couple other ones. So these tools are fantastic. And if you want to take a picture of the slide, the notebooks will actually be at the very last link. And I don't know if you guys can read that well or not. But it's clicksecurity.github.io/data_hacking.
If you just go to GitHub and you type in data hacking, it'll be one of the first links.
Even better. All right. Okay. So we're going to take a look at 2 use cases today, primarily because we thought they were pretty interesting to us, and second, they might be interesting to everybody else. So the first one we're going to look at is SQL detection, right? So given a random string, how can I determine that it has tokens or patterns in it that might indicate that someone's trying to slip one past the goalie? So our main goal when setting out to do this was to do this without regular expressions. Second is browser fingerprinting. Both POF and Bro have capabilities to say, hey, wait a second, I think this browser connection is lying to me. That's awesome, they've got some good signatures. However, there's always room for more signatures. So we're going to look at some ways that you can generate your own as well as run this type of analysis in your own environment. All right, so, this is just a brief, this is what the data hacking page looks like on GitHub. So we've got everything up there. And now, all right, sweet. So now onto SQL injection. Everybody in here familiar with SQL injection? Anybody not understand? Oh, okay, fine. So brief introduction to SQL injection. Someone tries to escape or an SQL command via a web app or some other kind of application to cause the original query to be changed to maybe dump information or execute commands locally. The idea is, with everything else, is to cause the system to do something it wasn't designed or intended to do. So for this, again, we use SQL map and JBroFuzz to actually generate a whole bunch of strings that are known for SQL injection, right? These are known tools that people run to say, hey, is my app vulnerable to SQL injection? And then we use the SQL Python or SQL parse Python library to go ahead and pull this information back out to do analysis. Is that mostly readable for you guys? Okay, cool. So this is, we'll skip all this. This is just setting up code in iPython so we can get pretty graphs later on. So, okay, one of the most important things, obviously, when doing data analysis is to get data. The second most important thing is to understand it and to be able to kind of get it into a form that is useful for the analysis. So that's all this really does right here, is just structures it up, and it gives on the bottom, I'll scroll up to the top, kind of a final count. So we have, in this case, pre-tagged data, right? We have almost 13,000 rows that came from these different SQL injection tools. And then we spent some time scouring GitHub and Google and looking for examples of legitimate SQL queries so we would have a legitimate set to test against as well.
And the other thing to note here is just, in that few lines of Python, we went from a raw, either Bro log or a CSV file, and we loaded it into a pandas data frame. And a pandas data frame is kind of the Python equivalent of an R data frame or a MATLAB data frame. It's basically a dictionary of series, so that each column, in some sense, is named, and then it's often stored as a NumPy array underneath. But all of that really means that you're one really good step towards analysis. So once you get it into a pandas data frame, you kind of open up the world to a large set of Python modules, statistics modules, scikit-learn, NumPy, SciPy. Once you've transferred your data into a Python data frame, it really kind of opens up the door for all of these different packages. And so, Pandas is just a great toolkit, and I highly recommend it. It kind of changes the way you think about data and how you organize it.
That's a good point. So just kind of a peek into some of the things that were generated by SQL map and JFuzz Bro. Obviously, you can see, right, trying to run XP command shell, trying to create different users on the system. So this is just a way for us to say, oh, okay, the data loaded correctly. So this is using SQL parse, and what SQL parse does is it kind of gives us a generic representation of the SQL string, right? So we can take something that's kind of the escape sequence, and then you've got exec, XP command shell followed by a ping command, and it breaks it up into these various data types that it believes it is. Is it 100% accurate? No. Is it, is it good enough? Most definitely. Is it really good? Yeah, it's actually kind of nice. So we get these different tokens that represent kind of the generic form of the strings that we have in our SQL injection statements.
And this becomes really important later on because you don't want to be doing a regex match on particular tokens and particular strings and, oh, did they do this delimiter or this identifier? I mean, you kind of want to take it, you want to do a data transformation to kind of this more conceptual space around, okay, what are the kinds of things that this SQL statement is trying to accomplish? And SQL parse does a good job of that.
So this is just a setup for later on in the notebook. One thing to note, when we talk about n-grams, in this case, we're not talking about substrings. We're actually talking about, we'll use the term feature vector to describe the parsed SQL, and it's a vector of these different tokens. When we talk about n-grams, we're saying the number of tokens in that vector. So an n-gram of 3, for example, on this first one, would be single identifier and float. That would be one possible n-gram of length 3.
And for those who aren't familiar with n-grams are typically done on strings. And so you can imagine, I have a big sentence and I'm kind of breaking things up into tuples. Either, I'm looking at every 3 characters and kind of sliding a window long, right? And that's called a 3 n-gram. And n-grams actually give you a sense of kind of more semantics. And in this case, for SQL statements, they're kind of saying, not only am I looking at individual tokens, but I'm looking at sets of tokens, and that kind of becomes, again, a kind of a higher level thing where what are these sets of tokens trying to accomplish from an SQL perspective?
No, precisely.
Yep.
So this is kind of where we begin to get into more of the statistical side of things. As you can see on the top, we're running this thing called the g-test. What the g-test basically does is it tells us the probability of something that's likely to occur, or in this case, maybe not likely to occur in something else.
So g-test is related to kind of a chi-squared test or Fisher's exact test. It's basically an independence measure. And what you can do is you can say, well, if I have a set of malicious SQL statements and a set of legit SQL statements, g-test will basically look at all of the tokens, and in this case, n-grams. And you'll notice one of the things we did is we kind of just blasted the n-grams and then just threw them all at the statistics. We didn't say, we want 1 grams or 2 grams or 3 grams. We just computed them all and then let the statistics decide, hey, for this training set, I'm going to tell you what are the most meaningful differentiators. And in some case, it was just a 1 token. In some case, it was a set of 2 tokens. And in other cases, it was 3 tokens. I don't know if we have a picture of that.
So yeah, it's slightly cut off, unfortunately.
You might control minus or something? Or command minus?
Oh yeah, that's a good point. Maybe. There we go.
So g-test just said, okay, great. Given the set of tokens and sequences, here were the most meaningful differentiators between malicious and legit.
So, for example, and we can run through a bunch of these. Slightly below, we would expect to see just the identifier, right, the n-gram of length 1 single, significantly more times in a malicious statement than we would in a legitimate statement. So, I don't know, we'd expect to see, basically 99% of malicious and less than 1% of legitimate. So this is kind of a much better way to view that type of data, right? We can begin to say, all right, here are the breakouts. So the same exact n-grams that we listed in the table, but instead of actually looking at the numbers, let's look at how they lay out visually. So from here, we know, going from left to right, in the red, we have the most common ones to be found in the malicious set. So we expect an n-gram of single to be found, and then another n-gram of single identifier to be found, right? And again, once again, these are all kind of those tokenized SQL statements into a slightly more generic form. Then what the green represents, though, is the ones that are statistically not expected to be there. So kind of at a first pass, we could say, hey, maybe this is a signature, right? If we see a token of single in a string, then maybe that string is some amount significantly more likely to be SQL injection, whereas if it contains, you know, the n-gram of keyword identifier, it's significantly less. So once again, this is just kind of going through and putting the sequences in the data frame. And then from here, this is where we begin to look at things. So we've got the string keyword DML, this n-gram, and we're saying just show us what's in them. And I don't know if it's a little bit easier if I...
Actually, this one right there is interesting, right? So
Oh, yeah, go ahead.
Oh, so this data frame is interesting because this is coming out of the statistics. The stats is basically saying this sequence is the one that's most identified with malicious SQL statements. And here, kind of in the very first row that says raw SQL, you can see examples of the SQL statements that the statistics are identifying as, yes, you know, these are highly correlated with malicious features. And if you look at the statements, you can kind of see, yes, you know, those you know, kind of intuitively, those look like SQL injections.
That's a good point. They generally look bad. So we can run through a couple more. Right, these ones generally look good. However, there's a large set of these that have this keyword DML pattern, and there's also a lot of malicious ones. So kind of delving into the data a little bit, we noticed that one of the tools was tacking on a bunch of nulls to try and figure out column width, so it kind of skewed that part, and this is likely where, right, some signature matching might fall flat on its face. Right, so once again, here's another one, this keyword identifier, as we saw. Let me scroll up. This is where iPython gets interesting. I can't really. It's this row right here down at the bottom. So it's one of the less or least likely ones to appear in an actual SQL injection statement. But clearly when we ask the data and we say, hey, what has this tag? It goes, oh, there's actually a bunch of these in the malicious ones. So again, maybe not the best way to just rely on pure statistical analysis. Show us what's least likely and what's most likely, and let us build signatures or regular expressions over that. So what else can we do? Yeah.
You got to talk about it.
He had a note in the notebook. Is like, we need to find a hilarious picture. So I simply searched Google Images for hilarious, and this was one of the very first results. It doesn't have anything to do with SQL injection, but I love it, and despite Brian's protests, I said it's staying in.
That's awesome.
So from here, we decided to play buzzword bingo a little bit more, and we took kind of the easy way out, and we said, let's calculate length and entropy, because who doesn't love length and entropy? As it turns out, you know, we kind of looked at those, and they were all over the map. So while not entirely interesting, I'll let Brian talk about that in a little bit more. So this is one of the ones that I really, really want Brian to talk about. You can even see we got a little note in the notebook to talk about the wizardry. So one of the reasons this is entirely important is there's a lot of different ways to go from, all right, I've got my data, and now I've got structured data, and now I have a basic feeling for the data, but now I want to do something with it. And this is kind of part of the notebook that really takes it from one domain to the other, so you should just dig in, dude.
All right, so you know, we talked about the pandas data frames and about how, you know, putting your data into these data frames really gets you one good step towards kind of all of these analytic options. And so, you know, Mike talked about, oh, we just, you know, just for fun, we kind of computed length and entropy, and you can see in this data frame that we've taken, you know, length, we've taken entropy, we've taken the statistics on the G-scores around whether you're matching malicious n-grams. We've taken the statistics on the G-scores around whether you're matching legit n-grams, and we've just kind of tacked those on as columns into our data frame. And even though it seems, I don't know, kind of provincial, these 4 columns then, you know, kind of set the stage for kind of these deeper analytics, both statistics and in this case, you know, kind of we're going to use a random forest machine learning algorithm. So the thing to take away here is that, you know, we did kind of a transformation that isn't always intuitive, right? So we went from what's called sparse data. So I have a set of tokens, right? So, you know, I'm looking at just SQL n-grams, and those all become tokens. And through the statistics and through looking at, you know, oh, if I'm an SQL statement, you know, how many of these malicious n-grams do I have, and how many of these legit n-grams do I have? That got transformed into, you know, kind of this numeric, kind of continuous data, and that's a lot more well-suited towards a broader range of statistical algorithms and machine learning.
So I was just gonna say, so what the number in the malicious G or the legit underscore G column mean? So we computed all the G-test scores for all the different n-grams, added them all together, and took the average. So that's kind of the statistical number of, hey, this is about how important these n-grams are that appear in this SQL statement. So it's the way to take that sparse data and move it into something more dense that's more suited towards actual, well, different kinds of analysis, the kind that we wanted to do.
Right. And, you know, there's a lot of detail here, and that's why we're providing the notebooks and the GitHub, so people can always go to the website and kind of dive in. One of the things to do whenever you have, you know, kind of these variables is get a good sense and actually look at the variables. Look at their distributions. So box plot is a nice way to look at distributions. So here, you know, a box plot just shows quartiles. So, you know, the red bar is the mean. You know, the thing underneath it is the second quartile, and this little whisker here is the first quartile. So it gives you a sense for the distribution of the data over some range. And as Mike mentioned, you know, we kind of threw in some variables just to kind of see, you know, are these, you know, do these variables help differentiate between you know, malicious SQL statements and legit ones? And, you know, the length, really nothing there. Oddly enough, for entropy, you know, malicious has a skewed entropy distribution that's lower than legit, and I think it's because they do a lot of repeated tokens, right? And so you know, with other use cases, you're like, ooh, high entropy bad, right? In this case, you know, low entropy bad, because they're just putting in padding and they're trying to you know, do frame testing or whatever it might be. And then here we're just kind of looking at some nice plots. And again, one of the things to take away here is, you know, yeah, it's you know, 8 or 9 lines of Python, but you know, in 8 or 9 lines, I'm making this really nice plot. I'm embedding it into my Python script, and we're just looking at whether these new variables that we've created, you know, can help differentiate between one type of SQL statement and another. Okay, so you know, we looked at kind of all these different variables. So this right here, and I'm gonna hit Command plus a couple times just so that we can zoom in. This right here, I feel particularly passionate about, because this is kind of the Rosetta Stone between Python world, you know, kind of arrays, and then matrix world, where you can employ kind of all of these really nice algorithms from things like scikit-learn. So with a data frame, you can literally just pick your columns and say as matrix, and this becomes an X matrix. And so, you know, a matrix is just a formalized way of capturing, you know, a large set of rows and columns. But you know, it has to be in the exact right form. And so when you're dealing with things like scikit-learn, this is the kind of terminology they use. They'll use X matrix with a capital X for their feature matrix, and they'll use Y vector with a small y for your labels. So if I have labels, that just becomes an array, and I make a Y vector for that. And once you create this X matrix and Y vector, you are now locked and loaded. You can literally avail yourself of dozens of really deep analytic you know, methods in these kind of deeper toolkits. And you can see, you know, we pulled in scikit-learn, we pulled in a random forest classifier, which is currently kind of like, hey, you know, if it's extremely robust for different kinds of data and distributions, and it seems to work fairly well. It doesn't overfit. So overfitting is a big issue depending on the machine learning algorithm you're using. So random forest does a really good job of the way it builds, you know, its forest of trees tends to be robust around avoiding overfitting. And so a couple of lines here, and we're done. So we actually did a cross. This is called tenfold cross validation. And this is kind of the standard way of testing the performance, the predictive performance of your machine learning algorithm. And you can see that we got 99% accuracy. So these are all numbers here that say, oh, you know, I'm going to randomly take part of your data as training, and then I'm going to leave the rest of it as testing, and then I'm going to do that 10 times, and then I'm going to give you the results for all of those tests. And that's called tenfold cross-validation.
What we chose is the feature vector. Scroll up just a second, right? We wanted to see what effect length, entropy, this token, excuse me, this token number, how many n-grams of the tokenized SQL string appeared in each, to see how that combination of those four features could actually lead to a useful output, right? So there are many other things that we could have computed as well. This is what we chose. Is it 100% correct? Probably not, but hopefully, right, it stimulates some other ideas both for us and everybody else.
And it's a good point. So the other thing is, you know, the notebook kind of leads you through. You know, here's how I loaded in the data from a bro log. You know, here's how I put it into a data frame. Here's how I took my data frame and converted it to an X matrix. And so you could take the same concepts and you know, kind of apply it to your own data. So one of the things we wanted to do is, you know, this 99% number, I don't know, that feels slightly dissatisfying, right? So you really want to get a much more visceral, concrete sense around, okay, so when I did the classification, you know, how many legit things got classified as malicious, how many malicious things got classified as legit. So those terms are called false positive, false negative, and the best way to look at that is not with an accuracy number. The best way to look at it is with a confusion matrix. So confusion matrix sounds complex, but it's really just looking at these four quadrants. So here, and your confusion matrix, you always want it to have this, you know, kind of high diagonal. So here it's saying, you know, that 98.9% of the legit stuff got classified as legit. 99.69% of them, and then these off diagonals are showing you, okay, what is, you know, this is my false positive, so what is the legit stuff that got classified as malicious? And then my false negative is what is the malicious stuff that got classified as legit? So even though 1% and 99% accuracy, woo, that sounds awesome. You know, the reality here is if you're processing millions of SQL statements, 1%, you know, that's suddenly you're looking at maybe 10,000 statements, right? And so even though 1% sounds good, kind of on the surface, it's definitely a place for improvement. And so one of the things you can do with these classifiers, they have a prediction method. They'll just give you kind of a 0 or 1. They also have a prediction probability method that will give you a continuous score between 0 and 1. And that's really useful for minimizing your false positives. Because you can say, look, I'm happy for you to miss some as long as you're not being noisy and you're not, sending all these false positives. And so you can kind of tune that probability prediction. Okay, so probably we're running a little long. One of the things that's nice here is you can ask the machine learning algorithm, hey, in the features that I gave you, what did you think were the most important in differentiating? And you can see that length and entropy, they were kind of close to 0. It didn't actually think that those features were that important. Okay, so here we're looking at, we can kind of look at a couple of the misclassifications. And at the bottom work is you have a training script that you run on a jillion samples, and then you make a model, and then you pickle it. So you just take and this is all in the notebook. You just take the scikit-learn model, you pickle it, and then in an evaluation script, you unpickle it, and then you evaluate new samples that are streaming in. It actually shows you exactly how to do that. And so, in fact, this is a little baby version of the entire notebook. So this is what your evaluation script looks like. It's literally this small. The SQL statement comes in, you send it to the parser, you send it to the n-gram extraction, you do these aggregations for the G and L, you call predict, and this is that CLF there is the classifier. So you just call predict, and then it spits it out. And in fact, we did a little, we just made some little joke SQL statements here to see whether the algorithm predicted whether it was legit or malicious. And my buddy Dorsey here, we always make fun of his mom, so I promised that we would put a reference into his mom. Okay, so sorry, kind of rambled on there, but there's lots of cool work here on SQL injection, so we included that material.
Quick question. You did note somewhere, but I don't know if you expanded on it. You had a small sample of legit calls, vice, malicious calls.
Yes.
Would having a larger sample of legit calls affect your numbers?
Great question. Let me repeat it. The question was that we had 13,000 malicious samples, and we only had 1,000 legitimate samples. Does that bias our results, and would we get better results if we had more legit samples? That was the question? Yes, good observation. In general, for machine learning and these kind of statistics, the more the better. And so, we gathered what we could given the time constraints, and it's actually harder in some cases to gather legit stuff than it is malicious stuff. So definitely, if gathering more legit samples would help the performance of the algorithm. Good question.
And that was just a quick deviation. That was kind of one of the reasons why we wanted to release these things for you guys to play with. I mean, if you're sitting on a wealth of really interesting data, right, maybe, you go home, you run it, and you say, hey, look, I found these new and better results because those guys on stage weren't 100% correct, and here's how we can improve what they did.
Yeah, and it's GitHub, so you can always contribute back.
Did you look at adjacent statements as a feature? So, for example, if you had like blind SQL injection where someone's doing like binary searching, the adjacent statements might be pretty important.
Agreed. I guess the question is, did we look at adjacent statements if someone's doing blind SQL injection to see if there were any correlation or relationship between multiple statements? The answer is no, we didn't, but I agree that probably would be super interesting to take a look at.
Good observation.
Do you think there might be some bias in your results based on the data that you're using as input? So it looks like you have complete SQL statements for legit stuff, and you have partial statements for injections, which seems like there might be some issues. Like that might cause an entropy. The basic statute might be different because doing partial commands versus full commands.
Yeah. Good observation. So sample bias is always an issue. So when you're doing statistics and machine learning, one of the things to always watch out for is sample bias. is my sample somehow skewed in a way that's actually making my results look better or worse than they should? And I think the observation you're making is, in this case, it probably makes our results look better than they should because we kind of have this mix and match of statements. So the answer is that's an issue. Sample bias is always an issue. We haven't formally addressed it in this case. The one thing I'll throw out is things like the machine learning totally tossed those out anyway. It basically said from a feature importance perspective, they weren't important. So it's mostly looking at the statistics around the G-test independence scores. But it's a good observation, and probably to be, it probably makes our results a little better than maybe they should be.
Do you want to jump to the next notebook? Yep. And then okay, cool. So we've got the second use case, and then we'll circle back around for questions on both, if that's okay. And since apparently we have no hard time limit, as we were informed about earlier, we're happy to stick around and answer questions. And
Our DVD recordings run out at 63 minutes.
okay, that's good enough. So I think we can do that. Okay. Oh, okay. So with browser fingerprinting, once again, hey, given a HTTP request, how can I determine if it belonged to a legitimate browser or a piece of malware? That's kind of what we're going to set out to answer with this. One of the first things that we did was we sat on a network and we collected a whole bunch of HTTP requests. We used Bro for that. In the same GitHub repository, you can download the Bro script that'll actually print out all the header values, the headers and their values. So once again, you can generate your own data, you can go grab the code, and you'll be able to run this entire thing at home. You don't need, as a side note, you don't need super powerful computers to do this in most instances. We actually did all the research and computation on our laptops, so it really isn't awful. The other thing that we did at the end, I'd like to say thanks to Contagio for having a really sweet malware dump. They have all the great PCAPs, so we were able to kind of grab some malicious PCAPs and see if any of those applied to what we were able to learn. So we'll kind of go a little bit faster on this one just so we can get through and answer more questions. Once again, reading the data from this one, we actually had 100,000 lines of Prolog that we were going to digest. Now granted, that was both client and server, so we pruned those down to client only. And that's really all this does, is it just sets up the client event. In the Bro script itself, it prints out the headers and their values as key value pairs in a JSON section. So we simply convert that JSON section once again to our favorite word, feature vector, and put it in a pandas data frame. This one I really have to point out, I groaned at it. So
Best picture ever. Come on, short agent. Come
right,
on,
Zach.
that's cute.
Thank you. Thank you so much. So one of the things we tried with this idea of a short agent is everybody has seen user agent strings, and they're loud and they're gnarly and there's just a lot of crap in them. So we tried to figure out if there was a way we could kind of condense the model by saying, well, these are common features in a user agent string that we should pay attention to. Once again, we started off with a couple guesses. Some worked better than others. We stuck with the ones that worked better. Is there room for improvement? Always. So what we did, though, as you can see here, we took this user agent, the super long multi-line thing, and just simply compressed it down into features that we thought were important, right? This works against multiple browsers, so it doesn't have to be just Internet Explorer. It can be Firefox or Chrome or Opera. You'll see a couple of these actually peppered through the data set. And all this function does is just simply computes the short agent. We also throw out a couple different things that we don't necessarily want. So all the .NET stuff, we didn't feel like we needed the full version. We just kept major and minor. So once again, taking a peek at the data. I'll make this a little bit easier, hopefully. So this is kind of a mapping of the short agent to the types of header permutations that we see. So you can see for WebDAV, right, it's got there's a whole lot of overlap, right? They generally all start with the same thing, and they kind of have this same order-ish, except for that you can kind of set these don't cares for particular headers like refer or cookie because they may or may not exist. But this is, so we've got Microsoft Office, we've got a bunch of different kinds of Internet Explorer, and it's all terribly exciting. So once again, we kind of wanted to see this kind of other grouping of short agents, kind of what are we dealing with. So we have this other, and we have Internet Explorer, and we just kind of wanted to get a rough feel for actually what was in our data set. And you can kind of see in some of the short agents, right, we still keep things like toolbars right there, and there's another one up here, because they could possibly change browser behavior, right, as a browser helper object.
And I think the numbers in the last column are all of the permutations associated with that agent. So it's all of the, I mean, part of what we're mapping here is that Internet Explorer in particular had this huge number of permutations associated with its requests, right? It was kind of all over the map.
That's a good point, yeah. And there's actually, this is my favorite plot. You want to?
Oh yeah, so this plot, again, is another box plot. It's just showing the distribution of the number of permutations here grouped by, in this case, whether the agent was an Internet Explorer agent or some other agent. And you can see that other agents kind of have this fairly well-defined, okay, I have a couple of different permutations of how I'm making requests, but IE is all over the map. And that's part of the challenge we have, right? I mean, if you have an agent that's all over the map, then how do you possibly make, a signature for that agent?
So here we just kind of, and we said for a given permutation, what short agents does it map to? And you can already see right in the top of this table, the second entry has this one header permutation, this accept encoding, user agent host connection cookie, maps to 6 different short agents, right? So you can see in the data there's kind of this really weird overlap of stuff. And furthermore, Internet Explorer doesn't necessarily make this any easier with its compatibility modes and all that other kind of really awesome things it does to make users' lives easier. So this was one of our bigger challenges was, okay, we've got, this many-to-one and this one-to-many mapping. How do we deal with it? How can we make something useful come out of this? So that way, maybe we can find malware easily by saying, well, show me everything that I can, or most things that I can't identify on my network.
We got 10 minutes.
Okay, yeah, I saw that. So this is one of the things that we looked at too was doing a Levenstein distance, and I really like Brian's implementation of this. So I'm going to let him go on about why Levenstein is cool, but why our kind of modified Levenstein is slightly more interesting, maybe.
Okay, so
You gotta be quick though.
yes, I have to be quick. So I put this in here because, it seems like extremely challenging ground that we're on here. So given all of these different permutations, all these different agents, how do we do something meaningful? And we kind of pulled out quite a few different things here. But one of the things we thought would be interesting is, okay, well, can I group the permutations in a meaningful way, right? I mean, can I say, well, that yes, I have for Internet Explorer 7, I have 67 different permutations, but are 32 of them kind of the same, and then maybe the Internet Explorer goes into kind of a different mode, and then 16 of those are kind of the same. I mean, we wanted to bring some organization to how we looked at these things and how we might develop signatures for them, right? Because with 67 permutations, one regex is just going to be either amazingly overfit or amazingly general and just not work in any meaningful way. So I think I'm going to some of this I'm going to leave just for kind of exploration offline if people are interested. But Levenstein distance is an interesting way to think about it. So typically Levenstein is you're looking at strings and you're looking at characters within strings, and it's often called edit distance. So how many and Levenstein measures three things: additions, deletions, and then substitutions. So those are the three measures that it has. And so here, instead of using characters and strings, we're actually just using tokens and sequences. So you can see,
how that plays in with H clustering.
yeah. So so here is an example that hopefully you can see. So we have, these four kind of mocked up header requests, and the Levenstein distance is associated with them. I think it's important for people to understand what's happening here. So the distance between A and B is 1 because we deleted one token. The distance between B and C is 1 because we substituted one token. And then the distance between A and D is 2. And can someone tell me, as a user audience experience, why that is? Different order, right? And so cookie here got transferred to the beginning, but then accept and user agent and host all remain the same. And you can imagine the kind of bookkeeping associated with that, right? I mean, that last example really gives you a sense for, and they do this really cool bookkeeping kind of inside this two-dimensional matrix, and then you do this backpathing to actually look at the edit operations. And so I wanted to give you a sense for that. It's kind of a cool thing. And now, if you go to the data hacking repo, there's just a library, and you say, hey, give me the Levenstein distance of these things, and it pops it out. So without much time left, the way we're using this is as a similarity metric. So we're actually kind of taking all of the agent strings, we're computing these similarities. So here's an example, for this agent here, right? Here are the most similar header strings, and it kind of groups them up into pairings. And then, the thing that will just have to be, part of the fun exploration you do if you're interested offline is, now that you have those similarity pairings, you can actually take those similarity pairings and make a hierarchical cluster. So I can from the bottom up, I can take the things that are most similar and kind of weave those together and kind of into this hierarchical cluster. And it sounds complicated, and there's quite a bit of bookkeeping to it. But if you have a nice Python module that does it for you, that's what we do here. And so here's an example of that. And so this is one of the Safari agents, and we have this kind of cool viz here. So all of these header requests kind of are of the form host connection blah, and then at the bottom here it kind of has this weird one. It starts with accept refer, right? But you can see that hierarchical clustering just automatically pulled that out for you, right? And it's fairly detailed, right? I mean, it's not like a hard clustering like k-means or something. If I k-means 2 or something, what would that mean? But this all just came out as part of the natural, organic way that hierarchical clustering works. And here's one of the IE agents, and it's a lot more complicated, but it's cool. And in fact, what we're going to do is we're going to build regular expressions for each of these subtrees, because each subtree contains sequences that are kind of the most similar to each other out of all the sequences. And so that's what we did at the end of the day, is we took the hierarchical tree, built regular expressions, and then so what it means is, instead of building one regular expression that tries to capture all of the possible permutations of all of the header strings for that agent, we built a set of permutations kind of formally informed by the hierarchical tree itself. So the hierarchical tree said you should build one regex here, another here, because there's enough difference between these things so that it makes sense to have a set of regular expressions. So here we have a validation at the end, and so we, of course, part of the thing you do with the validation is you say, okay, well, I don't want it to alert on my training set, obviously. So so I ran it through the training set, 45,000 requests, no alerts. ran it through the Contagio, crime PCAP set. They had agents that we didn't, and so we're just matching on. We're just taking the agents that matched up, and we're testing our regular expressions against those agents. And there were 21 requests with the agents in our training set, and it hit on all 21 requests. So, this is definitely, we kind of qualify this. This is definitely a work in progress. I wouldn't take the results too seriously here. It's kind of a smaller training set, smaller test set. But, it's kind of some interesting material. Like, oh, it's a way of thinking about how you organize your data, right? Like, oh, I compute similarities, and then I compute hierarchical trees, and then that really organizes my data in a way that maybe I haven't thought about before, and hierarchical trees are amazingly useful at capturing both kind of broad categorization and then small similarities. So, on both levels, you might, from the top, you might want to say, well, how does this thing look? Are there 5 major groups, of my million rows, right? That's meaningful. And the other thing that's meaningful is I have a particular row. Show me the things that are most highly similar to that row. And hierarchical clustering gives you both of those levels. Okay, so we're out of time. Just for fun, I wanted to point out there was this really nice IPython notebook on generating regular expressions, and it was kind of based off this XKCD comic. So if you just Google XKCD regexp, the guy does this cool kind of genetically algorithm-based regular expressions. So ours aren't that fancy, but it's cool and it's in Python. So okay, so I think time for questions.
You want over there?
So have you compared your techniques against things like BrowseCat project or UAS parser project or anything like that?
So a lot of this work is mostly about exploring data analysis techniques and kind of broadening the things in your toolbox. Like, oh, things in my toolbox that I could use in these different ways. In this case, it wasn't so much about, hey, we're going to get to some performance metric and we're going to beat some commodity product.
So we didn't do any comparison there. The main point, digest the data so we can help or enable people to make more community contributions around 2 things that we're aware of and we like to use for detection, so that way we can kind of enhance those signature bases, so to speak. But I guess to repeat the question, did we look at or compare to anything from the BrowseCat project or
UAS parser.
UAF parser? UAS parser. Oh, okay. No, I haven't played with that one. So yeah, so we did not compare with BrowserCap or UAS parser. Thanks.
But those are both good resources, and maybe as a follow-on project we'll do that. Okay, additional questions?
So jumping back to the SQL injection part, can you incorporate that into a reverse proxy and just kind of see real-world results, maybe expose it to the internet and see what people do against it, test validation?
It's a good idea.
Would it be hard to incorporate into it?
It depends probably on, would it be hard to incorporate this work into a reverse proxy? It probably depends on what you're using for a reverse proxy. Something maybe like Bluecoat might be significantly harder where they're not as open, but something like Squid, I'll get in trouble for saying this, I don't imagine it would be terribly hard. And I'm sure those will come back to bite me in the ass. In the back.
The SQL injection, how did you guys get your data for that?
Where do we get the data for the SQL injection? So one of our friends actually ran jbrofuzz and SQL map and then extracted all of the data from those test runs. So that's where we got the malicious set. The legitimate set, we literally searched Google for like file type SQL and then through select create a couple other SQL verbs, generic real world data sample. So is it perfect? No. Is it what we had to play with? Yes.
When you were going to the cloud, when you guys were setting up your testing classification, were you guys labeling the data yourself or using
We took the fact that they came from, so how did we get the classification labels? We labeled malicious as ones that we ran from tools designed to pen test SQL injection, and then the ones that we found on the internet, they were generally associated with open source projects and whatnot, so we made the blanket assumption that they were going to be legitimate.
Do you guys do any, this is something that runs in the kitchen, is that when people looking together and exporting data, data scientists are coming along and working with us. Hey, I found something that seems to classify really well, but there isn't, something I've always recommended doing, running basically doing an analysis based on contemporary tools to figure out whether or not there's an actual, well, maybe they found something, but the performance isn't quite what it needs to be based on, like, if you're doing like a regular expression matching, snort might not be as effective, but it might be much quicker, you might be better off using larger, more complicated regexes as opposed to using something like that, which uses probably uses random memory.
Yeah, so I guess did we consider, maybe this is a summarization, did we consider the performance of the end tools that we hope to take the techniques and push them into as far as to guide our output so it's performant on those tools? Is that?
Yeah, because it's people will find something, they'll be like, okay, I first did that and I found something. I'm like, that's good. I mean, it's glad you found something, but is it any more effective than what's currently run against? Is there performance? It's not a criticism.
No, no, no.
You guys are basically doing, basically trying to say, hey, you can do this type of thing.
Exactly.
That's the part that people don't really make a jump to. Is like, I can find things. It's like, well, you kind of have to compare that.
Yeah.
Yeah, and I think that was his point too, around did we compare the browser fingerprinting to other solutions, and you know those comparisons are somewhat tedious, and they also tend, you know, you tend to have sample bias. So you know what are the samples that you're comparing against? You know, is it the samples that time? They're good observations, and you know, at this point, again, it's mostly just about exposing the technique, showing how the techniques get used in some nice kind of real-world use cases. You know, whether at the end of the day the techniques perform better from some absolute sense than commercial tools, you know, I have no idea.
There was some operational interest, so running things like POF and Bro on what they had kind of out of the box, so to speak, we found some lack of signatures or lack of things that would help make these type of use cases useful. So from that is kind of where we deviated and said, hey, I wonder if there's a way we can help feed back into these kinds of things to make it more useful for us and everybody else. But operationalizing this kind of stuff tends to be anywhere from a small pain in the ass to a completely giant one.
All right, good questions. Any more questions? Okay, we're wrapping
We're getting
up.
the wrap-up signal.
All right.
So thanks
Thank you
for
so
sticking
much.
around for the last presentation. Do you want me to? I'll just unplug. I don't know. Computers.